I want to show you about the reflecting properties of ellipses and parabolas, and this involves a concept called the focus, plural foci, if there's more than one. So first I want to look at an ellipse here. And I want to look at the reflecting properties of an ellipse. So let's say we have an elliptical pool table with a hole here, and it only has one hole on the entire pool table, and the ball is at the focus, at one focus, and the hole is at the other focus of the ellipse. So if I hit the ball, it bounces off that white point and it goes directly into the hole. So if I aim it right there, now what if I aimed it slightly differently? If I aimed it over here, it still goes in the hole. What if I aim it over here? It still goes in the hole. What if I aim it over here? It still goes in the hole. What if I aim it down here? What if I aim it way over here? It still goes in the hole. Alright, so no matter where I aim the ball, it goes directly into the hole from the focus. Now, it turns out if I move my ball anywhere besides on the focus and aim anywhere on the ellipse, it will never go in the hole, because only things that reflect from one focus hit off the ellipse and go directly into the other focus. Now, the other thing I want to show you is what is the relationship between the shape of the ellipse and the foci. So let me move. I'm going to make this a little smaller so it's easier to see. So if I were to move the foci closer and closer together, notice how the ellipse looks more round. And if the two foci are actually on top of each other, it's exactly a circle. If I were to move the two foci farther away from each other, it makes the ellipse more narrow. Okay, so more circular, more narrow, depending on where the foci are located in relationship to each other. Now, how do you find the foci? There's another video you can watch about how to draw an ellipse with two tacks and a string, but what we did in class was I drew two dots on the board, and I gave a piece of string to two students, and I had them hold the two ends of the string on the two dots, and then I stretched out this string, and I put a pen, a marker here, and I drew around. And when I drew, okay, so right now the string is stretched there. If I maybe drew over to here, the string would be stretched this way and so forth. But when I drew around, and that's probably not a super good drawing of where that string would be located, when I drew around this, I got an ellipse. Okay, that's not, oh well, let me try that again. Let me see if I can draw that a little better. So I got an ellipse, look kind of like this. Now what, the focus should look about the same on both sides. Alright, I'm going to try to make this look right. Alright, so we drew the ellipse, and so imagine like just pulling that string around all the way around, and I drew the ellipse attached at these 2 points, and then this point is moving. Now, like I said, there's a video that shows that better than I can describe it on here. If I were to stretch that string out, that black string, it turns out that the black string is exactly the width of the ellipse. So if I were to take this string, so let's say I had the string. So here's the string. It's exactly the width of the ellipse, but if I were to attach it to the two foci, which are right here, and stretch the string, it would stretch like this if I put it straight up. So what I want to show you is that the length from here to here is exactly the same as this length. Okay, so from the center all the way over to this vertex, and from the foci up to the top vertex, this length and this length. So I'm going to actually erase the other side so you can see better. So this length, the red length here, from here to here is the same as this length right here. If you didn't see the demonstration in class, you kind of have to take my word for that, but hopefully my explanation kind of helped explain that. This distance here is called the major radius. I'm going to put a capital M for this because we'll use a capital M to represent the major radius. So here's the major radius. It's the longer of the two. So this distance also then would be the major radius. from the focus, okay, so this is one of the foci, focus, all the way to this point over here. Now the other distance, this distance here, is called the minor radius. Well, I'll use a small m for that one. Minor radius. And I want to add a third radius. So we're going to take the radius from the center to the focus, and we're going to call this the focal radius. Now you can see that the right triangle formed by the there's a right triangle formed by the minor radius, the focal radius, and the major radius. And so we can use the Pythagorean theorem and say minor radius squared plus focal radius squared equals major radius squared. So using that relationship, and I'm just going to kind of abbreviate that here, minor radius squared plus focal radius squared is equal to major radius squared. We can fill in the numbers from this graph. So you can see from 0 out to here, this is 5 units. So we can say the major radius is 5 squared. The focal radius, and I think I'll color code this so it'll match what I have here, 5 squared. The focal radius is 4 squared. And the minor radius is 3 squared. And 3 squared plus 4 squared does equal 5 squared. What this would allow me to do is, if I know my major and my minor radius and my major radius, then I could put those to the Pythagorean theorem, and I could solve and find the focal radius. Or if I know what the focal radius is, and maybe I have a length of string here that I'm going to tie to them, I would know my major radius, because that would be half of this piece of string, and then I could figure out what the minor radius would be, and so forth. So let's say you wanted to make an elliptical table. First of all, you would make cross lines to represent, where perpendicular cross lines, and you would locate where you want the center of the table to be. And then you would determine the dimensions. Maybe I want it to be 6 feet long. So I could go mark 3 in this direction and 3 in that direction. I want it 2 feet wide. So I could mark 2 in this direction and 2 in this direction. And then I would want to make something to draw it with. Well, I could use 2 for the minor radius and 3 for the major radius, and I could figure out where to locate the focal radius from the center, and I could mark the 2 foci. Then I could cut a length of string that was the length of the major radius, tie it to the 2 foci, and draw the ellipse using that string and a marker or something, and I could make the template. The other thing I want you to remember is that something that originates at one focus always reflects to the other focus. Now there's an interesting story about that, and that has to do with Statuary Hall in Washington, D.C. So let me find my picture of Statuary Hall. Okay, so here's a picture of Statuary Hall. Statuary Hall has statues along the sides, and it has an elliptical ceiling. It's an elliptical shaped room with an elliptical ceiling. It turns out that if you stand directly below where the focus of that ellipse would be on the floor, and someone else stands where the other focus would be, you can whisper and hear each other perfectly. Former members of Congress, when this used to be an office building, found out about that and located their desk at one focus and put the waiting room for their office at the other focus, and then they were able to easily eavesdrop on people waiting in the outside office to see them and hear what they were saying. Okay, so let's go down to the bottom and look at one more example of finding the focal radius and plotting the foci. And it says it will not be a nice number this time. So let's locate, first of all, the major and minor radius. So we have, this direction is actually the minor radius because it's only 6 units long. And this is the major radius because it's 7 units long. Okay, so major and minor. Now, the foci are always in the same axis as the direction of the major axis. So my foci are going to be, here's the center point right here. They're going to be one's going to be above the center point on the major axis and one's going to be below the center point on the major axis. But I need to figure out how far away they'll be. So remember then that I can do minor squared plus focal radius squared equals major axis squared. So the minor squared in this case would be 6 squared plus f squared, what I'm trying to find out, equals 40, or 7 squared, which is 49. So if I solve for f, f squared would be 7 squared minus 6 squared, 49 minus 36, which is 13. So f is the square root of 13, which is about 3.6. So if I go 3.6 units up and down, this is the focal radius. Okay, so the focal radius is this direction, and we could see this point would be at 0, 3.6, and 0, negative 3.6. So if I were to actually, let me kind of add this red line back in for the major axis. If I were to connect the focus to the end of the minor axis, this distance here, 7, is exactly the same as this distance here. So this would also be the major axis here, which equals 7, and this equals 6, and then, oops, I wanted to put that in blue, this equals 6, and then this would equal about 3.6. Okay, so the other, and then the other focus would be down here. So there's one focus. I probably ought to put those in black so they're a little easier to see, and here's the other focus. Okay, so I'm going to stop and make a different video than for the focus of a parabola.